before we actually talk about machine learning, there are some data processing techniques that we are going to come back to, which is the notion of stationarity. As I discussed earlier, it is important that the features that we pump into a machine learning algorithm be stationary, and that's a technical term. Because, for example, you cannot use the price of Amazon or the price of the spider as a trading signal, right? Because 50 years ago, 10 years ago, spider might be half of what it is now, or Amazon might be 10 times less than what it is now. You cannot possibly use that price as a feature to predict what its return is going to be tomorrow. They're just totally irrelevant. So only stationary signal can be used. Now, features can be used. So an example of a stationary feature would be earnings, earnings per share. No, okay. So you might think, well, that's the price also suffer from arbitrariness, right? I mean, the price can be is very arbitrary. So if you are creating a machine learning algorithm to predict the return of every stock, you can certainly not use the price because they are arbitrary. You cannot compare the Amazon price with Apple's price with Microsoft price or with GM's price. They are totally different scale and arbitrary. So besides stationarity, the arbitrariness, the cross-sectional level of the price are also make it impossible to predict. So that's true. But what about earnings per share? Things such as PE ratio. They do suffer from this cross-sectional problem. Essentially, PE ratio, they might be comparable between one company to another, right? So, the PE ratio of Microsoft should be comparable to the PE ratio of Apple. You can use that PE ratio to decide if you trade Apple or Microsoft. But even things such as PE ratio might not be stationary. And actually, some researchers suggested that the PE ratio has increased in recent years because that inflation has been undercounted. So the official inflation figure may be below what really is. That might be one reason why PE ratio is now much higher than before. And secondly, it could be a very interesting research for a person called Jesse Livermore, which is a pseudonym, I should point out, but it's very famous in the financial trader sphere, suggested that the PE ratio is now inflated because the depreciation rate has been understated in these days. So all this reasoning lead to the fact that the PE ratio, even though they look like a normalized number, look like it should be comparable across different stocks, may not, however, be stationary in a time series, in a longitudinal manner, in a time series manner. And so the PE ratio in the 1960s cannot be used to predict tomorrow's return. You might think that, in the 1960s, the PE ratio for GM is 5, and whenever it goes over 5, we should short GM. And you look at the PE ratio of GM today, and you say, the PE ratio is 10 for GM today, and clearly much higher than 5, and we should short GM. That is the erroneous conclusion. That could be an erroneous conclusion because the PE ratio of just one company alone, such as GM, might not be stationary. They make what it was in the 1950s may not be comparable to the PE ratio of today. So even a simple thing like PE ratio need to be dealt with to make into a stationary time series in order to be used as a feature in machine learning. Now, one simple way to deal with this non-stationarity is simply to take the percent change in time. In other words, take the time difference. So, for example, we know that price is not stationary. So if you look at the returns, that is guaranteed to be stationary. Another way to do it is to take the log of price. The log of price is still non-stationary. right? If price is not stationary, the log of the price is still not stationary. Just taking the log won't make it stationary. But if you take the difference, time difference in the log price, that results in what is called log return, right? So instead of the usual percent return, which is what the academic call net return, log return is the difference in log price between time t and t plus 1, or time t minus 1 to t. That difference in log price is called log return, and that's also stationary, just like net return. Okay, so now, so that's, you say, well, that's simple. Everybody should just take the log of a quantity and take the difference, or take the percent difference, just like the usual way, and end of discussion. But the problem with that approach is that sometimes this differencing in time creates a big loss of information. That's what Lopez-DiPaolo suggests in the book, is that this is losing too much information. You're completely obliterating any information that the recent level of the price will tell you. So again, if you have become familiar with technical analysis, right? A lot of times, technical analysts would tell you to use moving average as a signal, right? Everybody's familiar with moving average or exponential moving average. Well, moving average is a non-stationary quantity, right? Because just because you take the moving average doesn't make a price series suddenly become stationary. But yet, many technical analysts would swear by it. So, well, you know, we have a moving average crossover to the upside. We should buy the breakout or something like that. Now, are they all stupid? Are they all spewing nonsense? Not necessarily. You know, I know a lot of technical analysts that are multi-millionaires, so clearly they know what they're doing. So, you know, things such as moving average or moving average crossover is not all nonsense. Yet, if you follow this, what we discussed, we say, oh, but it's not stationary. How can it be used as a signal? Well, it turns out that sometimes the level also conveys information. So we have a dilemma. On one hand, machine learning cannot deal with non-stationary features. On the other hand, we know that sometimes the level is informative in addition to the time difference. As many rich technical analysts, you know, practically everybody in the book, New Market Wizard by Jack Schreiber, is a technical trader, right? And they are all multimillionaires. They have beautiful homes. So how do we resolve this dichotomy? On one hand, we cannot use non-stationary data, and on the other hand, the level conveys meaning. Well, that's what Lopez-DiPaolo suggests in his book, and that is a technique called fractional differentiation. Fractional differentiation is a way to convert a non-stationary price series into a stationary time series, yet retaining some amount of the level information, just like you would do in taking moving average. So before we discuss this, let's look at what is the technical definition of stationarity. The technical definition of stationarity is that we assume a simple linear model relating the change of log price to the price. Or Y can be anything. It could be log price, or it could be PE ratio, or it could be earnings per share, it could be book value, whatever you have. But let's think of it for concreteness as log price. So the simplest model for these kind of price series is a simple linear one. In other words, we believe that the change in this quantity is a linear function of its past value. Delta y is k times y at t minus 1 plus some noise, right? So this is a very simple linear model. It cannot be simpler than that. Now, if this price series is a random walk, well, a random walk is not stationary, right? A random walk can go to infinity. Eventually, a random walk will go to infinity. So if you look at, if y is the log price can, you know, go up 10 times every decade, like Amazon. Or if a log price is a book value, again, it can go up 100 times over 10 years. It never ends. Presumably, one day maybe Amazon go bankrupt, we will suddenly go from 10 trillion to zero at some point. You never know, right? I mean, 50 years from now, maybe there won't be an Amazon. So, the book value and the lot price, those are random walks, and they're not stationary, far from it. But if it is a random walk, then clearly K is close to zero. Because a random walk, you cannot predict the change so easily based on the previous value, right? The definition of a random walk is that delta Y is just white noise. It cannot be related to the previous price. If it can be related to the previous price, it's not a random walk. So the stationarity test in statistics is to test whether K, this proportionality constant, is zero or not. Can we reject the null hypothesis that K is zero? If we can reject that, this price series is a stationary price series. If we cannot reject that, then this price series will be a if we can reject that, then it's a random walk. If we cannot reject that, it is a random walk. If we can reject that, it's stationary. And so on one of these on the notebook that is 3.01, we have a simple example of how to compute stationarity using Python.